Hello, my name is Adam Garcia. We're going to be going over microwave imaging and the medical application for this imaging. Microwaves are used to image electric bodies. They have long wavelengths, which enables a penetration into a diverse array of optically opaque materials. The majority associates microwave radar with target detection and traction. However, it has been used for remote sensing, such as weather patterns and images of planets, as you can see to the right. As you can see right here to the right, where we have an image of a storm. Biomedical imaging and diagnostics is a new application that still has many uncharted areas. Washington and Jacobi were the first people to use microwave imaging. They did experiments using microwave radiation to image canine kidneys. They were successful at this by producing 2D images. The images show that there was damaged tissue in the kidneys. They used two antennas, one was transmitting, one was receiving, and that they were facing each other. The image recorded on X and Y coordinates. They experimented with frequency domain of S parameters, performed both copolarized and cross-polarized measurements. They also did this in the time domain. However, there are still challenges today that were identified during the 70s and 80s. Another challenge was tissue problems. Skin is the first defense against microwave waves due to layers of fat and muscle that cause reflection and dissipation. The electrical properties of tissue exhibit strong dependence on frequency in microwave bands. The deeper the tissue, the harder it is for a microwave system to get an image like the liver. One approach to solve this problem for the microwave signal into the tissue is putting antennas and organ into a coupling liquid. Larson and Jacobi used this method. The only difference is the coupling liquid today is more sophisticated to provide the necessary energy. Another approach is to make microwave waves that directly couple power into the tissue. There is no loss in power unlike the previous approach. This means that there will be higher coupling efficiency and better sensitivity of the system. The more sensitivity in the microwave system and imaging means that it can detect smaller and low contrast objects. Another problem is image resolution. This is a problem because that produces the quality for the image. This is defined by the smallest distance between two small detectable objects that can be clearly identified. Resolution depends on the shortest wavelength and the microwave radiation through diffraction limit. This means that the resolution depends on the frequency of the microwave radiation, which is a small wavelength. However, the tissue imaging could cause less penetration depth. So right here, this is you can clearly see the different tissues here because this is a better quality image. Now we're using microwave imaging for breast cancer, as you can see with this contraption here and these images that were taken using that contraption. These people use multiple methods that were talked about, such as the coupling liquid method. This time, however, they used corn syrup for their experiment, which gave them good results. One thing that they found was the permittivity decreases and the conductivity increases with the increase of frequency. Another thing that they found was the total loss from corn syrup was 10.7 decibels, while water and saline had a loss of 180 and 165 decibels respectively. Dartmouth Group also made a clinical prototype, which is this image up here for microwave imaging. It will illuminate the breast with 16 antennas that will operate in the range of 300 megahertz and 1 gigahertz. During the test for 5 it took 10 to 15 minutes per breast. The breast was measured with different heights using the array of antennas. Using microwave tomography, the Dartmouth Group made a breast cancer detection system that is based on 3D FEM model. The study then had multiple development updates that allowed for data acquisition to be done in 2 minutes. The imaging process was done in 20 minutes, which would take hours. On this slide, this is very important because this is where we get all of our information, and it also relates to the class EMAG because we went over wave propagation, wave polarization, and plane waves as a topic, and this is kind of what these references are going over and how they affect detecting certain things in these tissues and skin.